Palladium catalysis has changed the way we make carbon-carbon bonds. At very low catalyst loadings, palladium complexes can efficiently catalyze the coupling of organohalides to a wide variety of organometallic reagents, forming carbon-carbon bonds like the one shown in red here. The organic halide in these reactions is most effectively an iodide or a bromide, with iodides more reactive. Some chlorides also work, but more slowly, and in some cases a triflate leaving group can also be effective, with reactivity that is intermediate between the iodide and the bromide. Notice that in all these examples, the halide is connected to an sp2 hybridized carbon atom. A wide variety of organometallic reaction partners can be used, and each specific reaction type is now associated with the name of the chemist or chemists who first pioneered its application in this context. So a palladium cross-coupling reaction using a Grignard reagent, which incorporates magnesium of course, is often referred to as a Kumada coupling. With an organozinc reagent, we have a Negishi coupling. While palladium couplings with organotin reagents like this one are named after Stili. When the organometallic reagent incorporates copper, the cross-coupling reaction bears the name of Sonogashira, while one of the most effective palladium-catalyzed couplings of all, using boronic acids and boronate esters, is known as the Suzuki coupling, or sometimes the Suzuki-Mayura coupling. Now the important thing isn't the small differences between the reactions with different organometallic components, or their different names for that matter. What's important is what they have in common. And whatever the organometallic reagent, the overall reaction mechanism is very similar. To begin the cycle, the palladium complex first loses two ligands, represented here as alpha ligand and most commonly organophosphines or simple anions like chloride or acetate. Losing these ligands frees up space and orbitals at the metal for an interaction with the organic halide. This equilibrium is reversible, but it's the PDL2 species at the top of the screen that initiates the reaction cycle. Indeed, in the first committed step, the organohalide, shown here as R1X, adds to palladium, a process known as oxidative addition because the oxidation state of palladium increases by 2. Next, the organometallic coupling partner is introduced. This process is known as transmetallation because the R2 group is transferred from one metal, a general M in this scheme, to another metal, palladium. Remember that M may be zinc, magnesium, boron, tin or copper, so there's some variation in the valency of the reagent, which is shown here as a divalent metal center. All the necessary pieces are now in position at palladium, but some reorganization is required so that the two groups to be coupled together are next to each other. Thus the next step is isomerization, to position R1 and R2 cis rather than trans to each other. Finally, formation of the new carbon-carbon bond occurs through a step that's known as reductive elimination. This is essentially a reversal of the oxidative addition step. Palladium is reduced, its formal oxidation state decreasing by 2. You'll notice that the palladium ligand complex PDL2 is regenerated and can start the whole cycle over again. There are some minor variations in this cycle with different organometallic reagents, zinc versus boron versus tin, etc., but the key steps and the overall cycle are the same. Palladium-catalyzed cross-coupling reactions are generally highly efficient processes. These reactions have been applied to great effect in fine chemical synthesis and manufacturing, delivering fast, selective, high-yielding, energy-efficient carbon-carbon bond formation. For example, in the synthesis of blockbuster drugs, such as these antihypertensive agents. Can you suggest building blocks that could be combined to make each of these molecules via palladium-catalyzed cross-coupling reactions?